and welcome everyone. I'm your host, Eric Novick, and I'm very excited to have Elea McDonald-Feit and Hongjoong Yi from Drexel joining us today. So welcome to the program, Elea and Hongjoong.
Glad to be here.
Let's dive into the intro. Elea, you're currently an associate professor of marketing at Drexel, but you started your career at GM. What did you do at GM?
So I got hired into the GM Research Labs, which is a staff of mostly PhD researchers. And I was in the operations research department. And my first project was actually designing production lines for stochastic failures of the machines on the production line. But I was a car girl and I found that really boring. So I eventually kind of migrated up to the supply chain. And my last job at GM was in the Advanced Vehicle Development Center, helping to make difficult engineering trade-offs. And we'll actually talk about that a little bit in the talk. You'll see more of kind of that flavor in the talk.
A lot of people transition from academia to industry, but you went the other direction. So tell us a bit about that and what prompted you to do that.
I actually got really interested in the thing we're talking about today, conjoint analysis. And I had a bunch of papers on my desk that I wanted to read about how to fit conjoint models with Bayesian tools. And I just never had the time within industry to kind of dive that deep. I kind of migrated into academia because I think of myself as a methods person. And you often don't have time in industry to really develop methods. You know, now that I'm a professor, I have the time to work on projects that take 2 or 3 years. So for instance, my paper Test and Enroll, which is about designing A/B tests and planning sample sizes for A/B tests, was kind of in the back of my mind for about 2 years. And then I was working on it steady for 2 years. And that kind of like development of a real method just takes more time than I found I ever had in industry.
Cool. So Hongjoong, now you just received your PhD from Drexel, so congratulations on that. And I understand you'll be starting at Clarkson as an associate professor in the fall. So tell us a bit about the kinds of things you're planning to work on, once you join Clarkson.
I plan to continue working on this paper with Elea. That's my first priority, and I'll be working on some other consumer behavior research in the domain of sensory marketing.
Great. Cool. So doing sort of continuation of some of the work you've done. What was the PhD program like? I know it's a long journey. What are some of the challenges? And would you recommend that to other people?
I found it the experience to be challenging, but also very nice. I think the most exciting part is we get to work on projects like this one, industry and academic collaboration research, and I really like it. So I get to see how this is done from both sides. And I think this is a very unique experience I get from Drexel.
Gotcha. And so the next question is actually for both of you relating to what you said. And that is, what are some of the fundamental differences between industrial R&D and academic research? What are some of the pros and cons of each? And Elea, maybe you can go first.
As a methods person, I'm often looking at, in an applied setting, I'm trying to figure out what is the simplest, most reliable way I can answer the question that the company has. I want to just make sure that by the end of the 90-day project or the 30-day project or whatever it is, I have some clear answer to the business question that they ask. And that often pushes me towards, simpler methods, simpler data, simpler surveys, just simple. In academic projects, you're often trying to sort of explore new methods, riskier methods, things that you haven't tried before. And so you have a little bit more space and time to work on those things. Of course, there's a price, and the price is that you have to work on problems that are going to be interesting to more than one company to kind of spread those costs out across, the extra. Basically, you could think of academia as like kind of pooling together resources to solve problems that would be interesting to lots of different companies. Cool. Do you have anything to add to that, Hongjoong? She's got more of the hands-on, since the project we're going to talk about, I never met the client. She was the client-facing part of that.
So I'm from the consumer behavior side of marketing research. How I see the difference between industry project and academic project is I think industry project cares more about the applied side. We want to see the effect and want to put it into use. Almost immediately, as soon as possible. But for academics like us, that we care more about the why part for consumer behavior researcher, we care about the mechanism. So this presentation you will see is a mix of modeling and consumer behavior, that we get the theories from the psychology side, and then we incorporate those into modeling. So I think this is the good side of both academic research and industry research.
All right, so why don't we jump right into it? I'll turn it over to Ellie now. She's going to go through her presentation. For the rest of you, please feel free to post your questions into Stage or Event, whichever you like. We'll collect them and hopefully get to some of those answers towards the end. So Ellie, take it away.
Great. So I'm going to be talking about this this project, the Gaussian process model for response time in conjoint surveys. This is joint work with Hongjun, who you just met, and Zia Zhao, who is an assistant professor of information systems at City University, Hong Kong. He couldn't make it because he's in Hong Kong. And this is the first time we've ever presented this work. So I apologize in advance if it's rough around the edges. And if you have ideas about how to improve it, we are absolutely all ears, because we're writing up a paper on this right now. I will probably be a little too distracted to follow the chat, but Hongjun will be able to answer questions in chat. But full disclosure, she didn't do the modeling. So if you have specific questions about the Bayesian modeling or the stand code or whatever, she might have to pass those on to me. But if you have questions about response time or conjoint surveys or the application, she is your expert, and she'll be there in the chat for you. So let's jump in. In planning the talk, I figured we would have a very broad audience today. So I thought I'd spend a little time sort of stepping back and telling you what a conjoint survey is so that you can understand that. And then I'll talk to you a little bit about response time in conjoint surveys and how we built a model to account for response time in conjoint surveys. And then I'll show you quickly an application that we did, which was for a local utility company here in Philadelphia that was exploring how people would choose between different electricity rate plans, different plans where the prices might go up or down. So put that in your head. We'll talk more about that later. But let's first jump in and talk about conjoint generally. What is a conjoint survey? I am going to go back to my GM days, and where, I said I finished my career at GM working in advanced vehicle development, where my role was essentially to advise chief engineers on difficult trade-offs that they were making when they were designing new products. So they might ask me a question like, should the minivan have a smaller cargo area so that we can give more legroom to passengers? Or should we make just make the whole thing larger? And we know that when we do that, the fuel economy will go down because bigger just is more mass to move around. But then there'll be more space for the kids' sports crap in the back. The answers to these questions kind of depend crucially on what it is that customers want. We could just go ask the customers what they want. There's a lot of sort of voice of the customer slogans out there. We'll just go talk to the customers and they'll tell us what cars they want. And better designers do spend time talking to potential customers. They ask them what they want, and that's kind of sort of helpful. The answer you usually get from a customer, if you ask them directly what they want, is that they want everything. And if you listen to them and build the car that they want, you'll end up with the Homer, which there was a whole episode of The Simpsons where Homer got to design his own car and they produced it. And this is the car that resulted, which was so expensive that Homer's family definitely couldn't afford it. What we can do instead is estimate customer preferences with conjoint surveys. So the idea is this: we ask customers to make somewhere between 8, 25, I've seen conjoint surveys with up to 50 tasks. These tasks are hypothetical product choices where we, by experimental design, vary the product attributes. You can see a question there. You're looking at 3 different minivans, and you can read what features and prices they have. And you have to answer which is the one that I would buy. So then we can collect that hypothetical choice data and use a model to infer customer preferences and features from the choices. And if you want a good introduction to conjoint in practice in general, I recommend this book by Orm and Shazan, it's called Becoming an Expert in Conjoint Analysis. So what is the model that we use? Well, it's not a standard linear regression model. Let me back up here. We can't do a standard linear regression model because the outcome is actually a multinomial response. It's like, which one did they pick of the 3 that were available? And so we don't have a a regular continuous outcome here. We have this multinomial outcome. So we use a multinomial regression. So this is the typical model that is used for conjoint surveys. So we say that the probability that you will choose alternative J in task I is this softmax function, this beta x. So beta is a vector of preferences, and x is a vector of like dummy codes for the features that we included in the experimental design. And so that beta x is kind of a measure of how much do you like the product. And then we have that for each alternative that's in the task. And then we take the softmax function of that, and that gives us a probability that you will pick J. So that defines our likelihood for the choices that we observe in the choice task. There's this second equation here, which is makes those beta parameters specific to each person, because your preferences for a minivan might be different than my preferences for a minivan. So we each have our own preference vector, and then we apply Bayesian shrinkage across those preference vectors. And this model was first proposed for conjoint analysis by Peter Lenk at the University of Michigan. And that hierarchical prior regularizes the estimates across respondents via Bayesian shrinkage. So it's basically, the model is saying that Conjoint and I might have different preferences for minivans, but they come from that common normal distribution. This beta X term can be interpreted as the utility in a random utility model, and that's the work of McFadden. So if you've seen this model from the econ side, you probably know the McFadden and Train as the names most closely connected to this model. Anyway, this should be familiar to some people in the audience, but that's the model that we're going to estimate with the hypothetical choices in the conjoint survey. If we estimate it, we might get parameter estimates that look like this. So this column here labeled estimate shows us the estimates. Now, these are estimates for dummy codes. So you have to know what the base level was in the experiment. In this case, the base level was 6 seats, and the coefficients for 7 and 8 are negative, which means that the base level of 6 seats is preferred to a 7 or 8 seat minivan. And anyone who's sat in the middle second row of a minivan knows exactly why that 6 seats is so much better. You space the kids out so that they can't beat each other up. More cargo space here is preferred to less. And then we get bigger coefficients on the engine and the price. So conventional engines are preferred to electric by a lot, and lower prices are preferred by a lot. So that might be the typical results that we would get from a conjoint study. If you want to estimate this model, there's plenty of commercial software available for it. I won't read through all this. I just wanted you to have the references there. But the most important thing might be for what we're going to talk about today is we can implement this model in STAN. And I have a tutorial on choice modeling in STAN that actually builds you, if you've never used STAN before, we'll walk you into STAN and build you up to estimating exactly the model I just showed you. It was written for a conference of conjoint analysis, conjoint survey people who weren't familiar with STAN. And so that might be useful to some of you if you need STAN code for this model. So that's my little mini background in conjoint. Here's the motivation for this project. Actually, to give you a little bit of background, we kind of hinted at it in the introduction. Hangjun was working on a project where she was fielding a conjoint study for this utility company in Philadelphia. I had been helping her with fitting the conjoint models and getting up to speed. So that little mini tutorial, I gave it to her in my office. The one you just saw, I gave to her in my office one day. She collected the data, and then we had the data. We actually showed the conjoint estimates to the company, and they went on and made their decisions. But we started to think about response time. And we were thinking about it this way. Data from a conjoint survey doesn't always provide very precise information about the parameters. These limited dependent variables, we only observe which one you pick. You don't rank them. We don't get ratings for each individual one that was there. We just have which one you picked. And that's great for the respondent because customers know how to pick things. That's what they do. That's essentially what consumers do in the real world. So they're very comfortable with the process. It makes the question very easy for them to answer. But it gives us kind of limited information about the parameters. But we can observe the response time for a choice at essentially zero cost. We actually just had the response times for all of these questions. And typically in conjoint practice, that response time data gets thrown away, or maybe you use it to identify a customer who is maybe going too fast and you think their hypothetical choices are a little bit suspicious, but it wasn't really used. People weren't using it. And we had this idea a few years ago that if we could relate the response time to features of the choice task, then we might be able to extract additional information about preferences from the response time itself. So that was the goal that we set out, and it turns out it works. Preview. Let's talk a little bit about features of the choice task that might be related to the response time. So let's look at a question ourselves. So here is two choice tasks. Hongjun made up this example because she was thinking a lot about jobs at the time. She was looking for a job. So suppose you were choosing between two job offers, and the first option was, or the first question, hypothetical question I gave you was task A. So you're looking at a survey, you're trying to evaluate these two jobs. You go, oh, they're exactly the same on the working time, and the offer one is higher. I'll take that one. Should be really fast, right? That was easy to process and also easy to decide because offer one dominates offer two. Now take a look at task B. It's got, wow, there's a lot going on there. Okay, it looks like offer one has more hours and a higher salary. Offer two has fewer hours and fewer days, but a lower salary. Okay. I've processed the question. That took me longer. Now I have to evaluate it. And the evaluation is kind of tough as well. Both for task B, both processing the task and evaluating the options once I actually have a chance to understand what they are both harder tasks, and they intuitively, that task should take me longer. So how do we sort of quantify this intuition that task A should be faster than task B? Well, first thing we have to kind of take off the table is the task order. That's the first feature that we propose is related to response time. And the reason we propose that feature is that plenty of other conjoint researchers who have studied response time in the past have noted that people just get faster as they go through the questions. They learn how to process the questions faster. Maybe they adopt decision heuristics, like always pick the cheaper one, that allow them to go faster through the task. So in some sense, we kind of need to control for the task order just to account for the fact that people are going to go faster as they proceed through the 14 tasks that they answered in our application. But the second one is actually motivated from decision field theory, which some of you may know. So decision field theory is kind of a set of models that propose that when people are faced with choices like this, they accumulate information according to some kind of stochastic process, like a Poisson process. And when they accumulate enough information, they make a decision. Those models, or some of those models, predict that when one alternative is much better than the other alternative, like in task A, you should be able to go much faster. And this finding has actually been confirmed in conjoint survey data in other studies where people were making choices, that when one option is much more attractive than the other option, then you should be able to make the decision more quickly. So that's the second feature of a choice task that we're going to relate to response time. I'm going to call it ZI2, but it's the absolute value of beta x1 minus beta x2. Now, keep in mind, I don't actually observe beta. I don't know what that is. That's actually something I'm going to estimate. And so I'm going to have to somehow incorporate the choice part of the model with the response time part of the model and estimate them simultaneously so that I can get an estimate of what this beta x might be. Two more features that we have looked at. The third feature, which I call ZI3, is just the average utility of the options that I show you. So people choose faster when they're faced with two attractive alternatives. And this comes out of the math psych literature that looks at people making choices. It's sometimes labeled approach when there's two things that I really like, it's easier to make the decision and I should be faster than when there's two things that I dislike. That motivates this idea that the average utility of the options I give you should make you, if that's high, if both of the minivans are very attractive, then you should be able to go faster. And then the last one is, this is a kind of a new one that we're proposing. So there is a lot of work using eye tracking that shows that when respondents doing these tasks, they do information search. They're looking at the question, and they will have more saccades when there are lots of attributes that are different, because they're just processing like, oh, how are these different, and trying to get that into their head, an understanding of how the two options differ on all the attributes. And we can kind of capture that quantitatively by saying, we're going to make this metric where we count the number of attributes that are different. So this K is indexing the rows down the choice question, the attributes of the products. And so we look at how many of those are different, but we weight them by the beta for that attribute. So when a alternative is very different on important attributes, this metric will be higher. And when all of the features are exactly the same, so if I give you a choice between two identical options, then this metric would be 0. And so that's going to be our fourth metric. We are still thinking about these sort of features of a choice task that we might relate to response time. So if you have ideas on that, we would be all ears. What I'm going to show you next is that we've developed a very flexible way to relate any feature that you can think of describing the choice task and why a choice task might be longer or shorter. We can relate to the response time that we observe. And the machinery we use for that won't be a surprise to any of the Bayesians in the crowd. We're going to use a Gaussian process to relate those 4 features, or any ones that you guys think of, but the 4 that we thought of, we're going to relate to the response time using a Gaussian process. And a Gaussian process is an approach for modeling any function, and it's extremely flexible. So this picture here shows a fitted Gaussian process with 2 inputs. So there's this input on the x-axis, this input on the y-axis, and then the output of the function is shown on the z-axis. And you can see it takes like all these kind of curvy shapes. And so in our case, we're going to say that the relationship between the 4 features we thought of and the response time follows a Gaussian process, so it can flexibly pick up any of these shapes. And that will allow us to pick up inverted U shapes, ceiling and floor effects, S shapes. You know, we could have just used the linear model here, but that would be very restrictive. We'd just be saying that the relationship between any one of these features, say the average utility and the response time, is a line, and the whole function is just a flat surface in this picture. That would be a linear model, but the Gaussian process allows us to pick up all this, potential curvature. We thought it was a really good application of the Gaussian process because we have this empirical literature that says these things ought to be related to response time, but a lot of times the experimental literature has only tested these things at a couple of different levels to show that the effect kind of generally holds, but the exact shape of it is unknown. And so this Gaussian process allows us to just explore that shape in our own data. A little bit more for the technical crowd on how the Gaussian process actually works. So none of this is innovative. This is kind of a standard Gaussian process setup. But the idea is that we take the whole vector of response times we observe, which in our conjoint survey will be the response time for every question that every respondent asked. So that's these response times that are kind of this big, long vector here. Like that's going to be a long vector if you've observed a lot of choices. And we say that whole vector follows a multivariate normal distribution with a mean 0 and this funky covariance structure K. So we're basically saying that whole thing follows a normal distribution, and that there is a covariance structure, and the covariance structure is a function of the distance between any 2 points on that z vector. So you can see the different that this here is kind of showing you. We're going to take along each dimension, each of the 4 features, of choice tasks that we have. We're going to compute basically this row here is a scaling factor. And so we're going to compute this like scaled distance between any 2 points. So we're saying if 2 questions have the same average utility and the same utility difference and the same attribute differences, and it's the same question number, then those should have about the same response time. And then this piece here is just some extra noise plus some noise, so that they'll have the same response time on average, but response times are going to be noisy around those averages. And so that's how the Gaussian process model is set up, basically. Here's our integrated model for choice and response time. You've seen all of this before, but I just thought I'd stick it all on one slide. So we've got our choice model with the softmax function that we saw earlier before, and then the hierarchical so that each person has their own preferences. And then we have this Gaussian process for the response time. It basically says that the 2 things should have similar response time if they're the same order, task order in the survey, if they have similar utility difference, if they have similar average utility, and if they have similar attribute difference. Those of you who are paying close attention will have noticed that I reversed these labels. Just they should be the other way. The first one is average utility. The second one is utility difference. The important thing about this slide is that this beta X appears both in the choice and in the response. So what we're saying is these underlying preferences are both related to how long it takes you to answer and what you will ultimately pick. And so it's that core, these beta Xi's that kind of link the two models together in kind of a principled way. And we're going to estimate them using Bayesian methods because hopefully lots of people in this talk know that Bayesian methods make it very easy to just add another equation to your model with a latent variable that connects between the 2 models. This is like a core theme in Bayesian inference. And I think this is a rather nice application of it to a marketing problem. This is implemented in Stan. This was all Zia's work. And I'm not going to go through the Stan code, just thought I'd put it here to show you once we get the paper written, which will be a couple more weeks, the Stan code will be in the appendix so that you can easily fit this model yourself if you like. So that is the Gaussian process model. We actually had this conjoint data for an electricity rate plan. So let me show you the survey is a little funky. The application is just odd, but that's because we were collaborating through the Drexel Solutions Institute, which that's our center at Drexel that facilitates, they're kind of like consulting plus projects where a company comes and they have some kind of business problem that they might ask of a consultant, but instead they work with us and a faculty member, which allows us to kind of dive a little deeper into the problems. It allows them to build a pipeline of talent that understands their problems. It's a way of promoting their company at the school among our students. You just get kind of a different answer from an academic than you would get from a consulting company. So they had a question about how people would respond to what's called a dynamic rate plan. So in essence, this is a rate plan where you have to pay more during the afternoon. And the reason that you would want to do this is because the afternoon is when we use lots of electricity. The air conditioners are running full blast right now in Philadelphia. What we want to do is incent customers to avoid using electricity during that period. So they shouldn't be running their dishwasher or washing their clothes or drying their hair, or other things that consume a lot of energy during this window. And so we make the price higher. So in this plan here, the price goes up to 15 cents per kilowatt hour from the period of 2 to 6 p.m. And you're choosing between that and one where the price goes up to 12 cents, so a little bit less, during the 5 hours from 2 to 7. So it's a slightly longer period. And then the base rate is also different. Some conjoint studies have a visual to try to explain the features to a customer. So I've got the attributes, they were listed up here, but they were also listed in this graph. I'm not sure the graph is the best way to present it to an average customer, but we were collaborating with some engineers and they really liked these graphs. So they were in the survey. I don't know if I would do that again if I was redesigning the survey. And we have data on 45 respondents who each answered 14 of these binary choice tasks. So that's the data. Here are the estimated parameters for the choice portion of the model and what they mean. So these numbers right here are telling us that on average, people care more about about the prices than they do about how long that peak duration is. They don't actually mind very much that extra hour. They still prefer the peak duration to be shorter, but the extra hour isn't as important as what the price is. So the prices were very important, with the off-peak rate being the most important. So customers think, we're getting some evidence that customers see that off-peak rate and they go, that's the more important thing because I can shift some of my electricity demand into that off-peak time, which is exactly what we want. These parameters here are telling us about the variance across the population of those individual preferences. So you can see those numbers are quite big. This is typically what we see in a conjoint study. People are kind of all over the map in how they individually rank the features. So some people really care about the peak duration and some people don't care about that peak duration. That's kind of typical conjoint sort of results, just to give you a flavor for them. Here I have the parameters of the Gaussian process. And honestly, the parameters are not particularly helpful. The sigma parameter is the easiest to interpret. That is basically the noise in the response time. So the standard deviation of the response times is about 5.6 seconds, which just means the response times are kind of all over the map. They vary quite a lot. And then this alpha and these rho parameters tell us how much on the average response time at any set of values of the features, the z's that I showed you before, how much the z's are related to the average response time. And you can see they're all significant and rather large, which just means, yes, we are finding that the features that we are proposing are very related to the response time. Let me actually show you a picture because that is an easier way to understand the relationship. So I am very open to suggestions on these pictures. We've been spending the last week or two trying to make these pictures really help people understand what's going on. And Zia was up all last night redoing these. So these are hot off the presses, but we're open to suggestions if others of you in the audience have worked with GPs before and have clever ways of showing them. So the issue here is we have 4 features and 1 response time. So this is what's called a multi-input GP. So what I'm going to do to show you the relationship between one feature and the response time, I'm going to condition on all of the others. So I'm just kind of take a slice through that multivariate space so that I can show you the relationships between things. So here's what they look like, but let's zoom in on one of them. So this plot here shows you the response time as a function of that utility difference that I was talking about. So this is how different are the 2 options that I showed you in terms of their overall goodness to you. And what we see here is that when there is a high utility difference, the response time goes way down. They get faster. They go from about a little over 12 seconds down to 9 seconds on average when I give them 2 things that are very, very different, where it's easy to make the decision, like the task A that I showed you before. And then we see as the things get closer and closer together, you slow down to a point, but there's a clear ceiling effect here. So we can say, once the things get kind of close enough that you have to think about it, it tends to be kind of around 12.5 seconds on average response time. So that's the utility difference metric. The second metric we have is the attribute differences. So this is how many of the attributes are different, weighted by the betas. And you can see here, when there are many attributes that are different, when this attribute difference metric gets high, the response time slows down, which is exactly what I said. When you're doing the processing step, just the processing step alone takes a little longer when you are dealing with a lot of attributes that are changing. The last one I'll show you is this overall attractiveness. So how good are the options on average that I have shown you? And you can see there, we actually get this counterintuitive finding, which is when the more attractive the options are, sorry, not counterintuitive, the more attractive the options are, the faster you get, which supports the hypothesis that I kind of laid out for you a couple slides ago. So the average utility, when the average utility goes up, the response time goes down, which is the approach effect that we talked about. That's kind of what the GP looks like. But we've played around with contour plots so that you can see 2 dimensions at the same time, or surface plots. I didn't put them in because we're just not quite happy with those. But if you have suggestions about how to visualize this, like I said, we're all ears. A few last things. One is This slide here, and I won't go into details, compares our model that I just proposed to a standard choice model that doesn't know about response time. And you can see that I won't go through all of it, but you can basically, what happens is that the response time, the preferences are basically the same between the two models. So by incorporating the response time in, we haven't screwed up our understanding of what people want to choose. We still are understanding choice pretty well. There's a couple things that are different though. One is the posteriors get tighter. So 0.202 versus 0.68. Exactly what our motivation was. We thought that we could learn more about people's preferences when we also use the response time. And it turns out that that is true. The other thing we see is that our understanding of heterogeneity changes. So we think there's more heterogeneity, there's more differences from one respondent to another. With this being 0.8 and this being 0.4. And let me kind of dive into that a little bit for you. So on this plot, I'm plotting the individual beta parameters. So I have 45 respondents, there's 3 betas, so there's a lot of points on this plot. And the gray box is my posterior interval. And on the x-axis is the standard model that only knows about your choice. And on this axis, we have the model that includes response time. And you see how the boxes are rectangles, horizontal rectangles? That means we have learned a lot more and our posteriors are much tighter when we include response time than when we don't. That's not universally true. You'll occasionally have a person that knowing the response time isn't helping you too much, but for most people, we're learning more about their individual preferences. And it's the individual preferences that were really deficient because we only have 14 responses. So it's pretty hard to estimate from the 14 responses your preferences for these different rate plan features or attributes. And so I think this plot is really cool. Last thing I wanted to show you is that we fit a model where we fit our response time model. That's the one you saw before in this first column here. Then we fit it again, but we didn't use the choice data at all. We just use the response time. So we're trying to fit your utility function from your response times alone. And you can see we get pretty darn close. So we actually do get a fairly rich understanding of people's preferences when they're making choices, when all we observe is just how long it took them to choose. And we don't know what they actually chose. And I think that's kind of, I'm going to end with that because I think it's kind of the coolest finding of all. These are, in case you were worried about our fits, whether the model actually fits the data well. Here we're reporting the out of sample predictive performance for the choice and for the response time. You can see basically I'm comparing the standard model to the model that we're proposing that includes response time. And when we put response time in, our predictions for choice actually get a little bit worse out of sample, but not horrible. And that's because we're now fitting betas that kind of compromise between the choices and the response time. And so we kind of lose a little bit when we do that in overall predictive fit. But the really remarkable one is this last line where that third model I showed you where we fit the response time model, but we don't have the choices. In that model, we actually get fairly good prediction of the choices, better than, this isn't great, but it's better than you would expect, given that we don't actually observe any of the choices. We can predict holdout choices, quite well. Better than random for sure. Random would be 0.5 on that metric. All right, just to summarize, that was a lot in a short amount of time. So we learned about conjoint surveys, which are a tool for understanding consumer preferences for attributes. We developed an integrated model of choice and response time that we can use with conjoint surveys, and that gives us a better understanding of response time and the decision-making mechanism. So this is actually a very interesting tool for exploring the relationship between response time and decisions generally. We applied it to a conjoint survey on electric rate plans. And what we find is that conjoint practitioners really should be collecting and using the response time because it will ultimately lead to better choice predictions. There's a few things we're still working on. So we are planning to fit this model with other conjoint sets. So if you have one, let us know. We're planning to extend the model. So I didn't mention this. Everything I talked about today was for binary choices. So the metrics that we've made for response time are all tailored around binary choices, which is what we have in this example data set. So we need to think a little bit more about how to extend this to choices that are made from 3 or more alternatives. And then we need to figure out better ways to visualize the multi-input GP. So if you have suggestions on that, I'm all ears. Thanks for taking the time to listen. I guess we have time for some questions, Eric?
Yes, we do. Thanks, Ellie. That was great. I appreciate the overview of your work here, and we're looking forward to the paper that I guess will be coming out soon. If the people in the audience, if you have any questions for Elea, Hanjun, please type them in to the chat. I will start us off with a couple of things, and one is sort of zoom out kind of prior to what you were discussing. So I think marketing researchers were pretty early adopters of Bayesian methods, right? For example, Sawtooth Software, which has been around for many years, has a built-in Gibbs sampler. Mm-hmm. And that's not true in other industries or other parts of academia necessarily. Why do you think that is?
So,
or am I right about this? I'm not.
You are absolutely right. So okay. Most doctoral students in marketing were reading Gelman's book by 1995.
So like a required
in that area. Not required, but many quant marketing students were maybe a little later, late 90s. So I started my PhD in 2003, and by then it was definitely like, here you go. There's another book by Rossi, Allenby, and McCullough that also is an introduction to Bayesian methods specifically for marketing. So those two books together were like, my summer reading after my first year as a quant marketing student in 2003. I think the reason is that we're modeling human behavior, and human behavior can be very, particular to the human that you're studying. And so by having hierarchical models, we could model heterogeneity well. And then there was a lot of follow-on work that showed that actually the products you would design once you understand that heterogeneity are very different than the products you would design if you just had one set of average preferences for the customers. So if people did that before the Bayesian methods came in, they would just fit a non-hierarchical multinomial logit and interpret those, and use those for share predictions. But there was a lot of follow-on work in marketing that said, time out. If you're going to have two products, then if you have a heterogeneous market, one's going to go low and one's going to go high in terms of features and prices. So it's very quickly see this sort of differentiated products thing happening. And so we were very, very quickly to adopt both on the practice side and on the academic side.
Interesting.
That paper I mentioned by Peter Lenk was one of the first Bayesian papers in marketing that kind of just pushed it all in. And that was published in 95.
So that the second question I have, maybe both you and Hanjun can weigh in on that. And you touched on this throughout your talk when you were showing sort of different graphs of inferences and predictions. My question is, like, when you present the output of these Bayesian models to the kind of the end users, which in this case was this utility company, what do you find the most useful both in terms of actually conveying the quantities of interest, but perhaps more importantly, kind of building trust in the model itself, right? Because a lot of these models, they have a lot of machinery in them, but GPs and these things are not like intuitively interpretable by themselves and so on. So, and we struggle with this ourselves, and I think everybody who works in the industry or academia, but I'm just wondering, what is your take on, like, what kinds of things are helpful there?
Yeah, do you want to start, Hangjun, with what you told the electric company, and then I'll sort of answer it more broadly?
Yeah, sure. So actually, we make this presentation multiple times to the client, all the way from the front line to the C-level executives. And every time when we explain the results, we use different ways, mainly on the visualization part. Because give you an example, when we talk to the marketing people or the frontline salespersons there, our presentation was much longer compared to the C-level presentation, which we got only 30 minutes to present the whole thing. So for that part, we did not expand on the modeling part. We directly tell them the results and what that means. And then we stop there and focus on the more important part to them, which is the next step, communication. How do we educate the customer? Those they're more curious about. Versus when we present to the marketing researcher there, which they know about Conjoint, and then they are curious about how we did that. Then we explain to them how we collected the data, how we designed the data, and what was the model exactly about. So that's the difference that we have.
Yeah, I think just to key off what Hangjun said, the most important thing for me is that you tell them what to do. And as analysts, we're often very reluctant to say that, but sometimes a decision maker can back into the analysis from the point where you just say directly, I think you should do X. You should use this rate plan. We think this is the best rate plan. And then let them ask and draw in how much of the why and how do you want, which is exactly the opposite of our training as analysts, right? We want to get into the gory details of the model. Specifically for these models, I never show the parameters because the relationship between parameters and what you might be interested in, like market share, is very unintuitive unless you've looked at the softmax function many times. So for me, it's intuitive, but even for Hangjun, it's less intuitive, that softmax function or how it works or how a table of parameter estimates would relate to something else. So I typically show market share predictions with uncertainty intervals as the main thing. And so like when I was at GM and working on Conjoint, they would want to see, I would show them two predictions, one for the car that they are currently planning to make against a key set of competitors. Here's what your market share would be. And then a second one, which is for the best car according to the survey. And then I tell them what the best car is. And that seems to be, like that's intimately tied to the decision they're making. They're trying to decide what features the car should have. And I'm telling them, here's what you're planning to do. And here's what you could do that would be better. Then they'll start asking questions from there and you kind of follow their lead.
That's really interesting. Which you said that, you're just going to tell them what to do, which that's what I would like to be told. Like I don't want to think about it, right? I also want to be told what to do. Often the models we have, they sort of produce the inferences that they have uncertainty. And so we tend to say, well, here's all the information, right? You figure this out. In your case, it's slightly different because you actually, you have an explicit model for the utility, right? So utility is kind of like in that model.
Yeah, but what isn't in the model is the loss function for the designer or the firm that's producing it.
Yes. So do you help them with, do you actually work on that at all in terms of trying to construct the loss function? Because ultimately, that would then, when you average that over the inferences, will give you sort of the Bayes optimal thing?
Yeah.
Or do you not bother?
Not in a formal way, but very much in an informal way.
Yeah,
so when I'm working with a decision maker closely, I try to understand their loss function.
Sure.
And the way I do that is my favorite question to ask any marketing analyst or marketing decision maker executive that I talk to is, what decisions weigh heavy on your mind? What's important when it comes to that decision? And just sort of let them lead me to sort of in a conversational way to understand their loss function. That I am trying to understand their loss function. I don't tell them what a loss function is. I just say, what decisions are you trying to make? What's important when you make those decisions? What do you think about when you make those decisions? And that can kind of help me. The best was when I was at GM and I was kind of steeped in the whole organization and I could just intuit the loss function from the organization as a whole. But I have done it formally. So that test and roll paper I mentioned, we actually explicitly lay out the profit from an A/B test for a particular type of A/B test. It might not be the kind of A/B test that everybody's running, but a lot of people are running these A/B tests where you can actually write out, this is the overall profit from both the test and the deployment stage of the A/B test. And then we find the optimal sample size according to that over some priors. And so that's the only time I've ever been able to do it in a completely formal and mathematical way, which is why that's one of my favorite, papers to talk about, because we were able to do that.
Yeah. I think that, what you just said sort of casually is great advice. And we often forget And I think we should always ask that question: what are the decisions, right, that you're trying to make, and how important is this decision versus that, and at least informally do that, right? Because that may have implications for the kind of model we're ultimately going to fit.
Yeah,
so
Hongjun, did you have that conversation with the electric company? What decision they were trying to make?
Yeah, so we have that conversation at the beginning of the project that kind of guided us through the entire process. Like ultimately, what do they want? So we were told that they are interested in knowing what features of electricity pricing plan is more important to a consumer. How do they better educate them, and what communication message they can use to advertise certain plans. So that was the main goal. And then from the result of the Conjoint model, we were able to tell them, see, this off-peak price is more important to people. If you want to advertise, you should probably be focusing more on that part instead of the other. And then we were able to tell them, so we give you all this prediction or estimate and how confident we are in telling you that. So I think that's more important to them instead of the details and nuances of the model development part.
All right. The last question I'll ask is and again, you touched on this a bit, but in terms of where do you want this model to go next, maybe comment on some of the areas where you think it's weak, or where are the extension points that you're hoping to develop with this particular one.
We need to figure out how to communicate the GP. That turned out to be much harder than I imagined, having seen other people present GPs. I didn't realize how much work they put into that. Another thing is this is just kind of the out of the box. This is literally the kernel that's in the stand manual, which we started with. And so there's a lot you can do with those kernels that might be better for our problems. That's something I'd like to think about a little bit more, is I think this is the right kernel, but maybe someone could convince me that I'm wrong. We didn't talk about this, but it's in the paper. We have a bunch of other biometrics. So we have galvanic skin response, we have electrodermal, EDA, galvanic skin response. And we have some brain measurements. What is it, Hongjun? Medial?
We have a medial prefrontal activity. We put a device on them while they're doing the conjoint survey.
Nice.
So our original idea was to try to bring all those measures in to help inform our understanding of people's choice making. It turns out the response time is really predictive of what people are choosing. It was we have a part in the paper where we compare all of those using linear models. So each one has its own linear model that gets added to the choice model. And just by far, the response time is very closely related. But one other little sort of sizzly tidbit. We also asked people how difficult the question was after, and that is also highly predictive. And you can almost do the same trick you did with response time with that question. But we didn't want to emphasize that because that actually is more burden on the respondent to have to think about how hard was it, where we can get the same information from the response time. So
yeah, and that's one of the reasons why we only have 45 responses, because that was a neuroimaging study. Yeah.
So Hongjun had to go in the lab, put the brain tracker on the person, nice. Put the galvanic skin response.
Thank you very much once again to Hongjun and to Ellie for joining us, and we'll see you guys next month.
Great. Thanks a lot, Eric.
Thank you.
Bye-bye.